sure.
Okay, let's go. Thanks.
Yeah, okay. Yeah, thanks for inviting me here. Yes, to share our recent work with you again, and also I'm looking forward to hear your feedbacks on our recent work. Yeah, so basically, during my name is Linhao, and this year is my final year of my PhD study. So basically, during my whole PhD study, I was focusing on how to combine the knowledge graph with large language model together. So basically, we want to like enhance the LLM with the power of the knowledge graph, and also we want to utilize the power of LLM to also to address some tasks that conventionally focused by the knowledge graph. So in the previous work, we have conducted some studies that focusing on utilizing the knowledge graph to enhance the reasoning of the LLMs. But in our current in this work, in today's work, I will present like how can we combine the power of the graph neural network, the graph foundation model, and with the power of the large language model. So we can design the kind of like a unifying reasoning model that powered by this kind of two strong deep learning method that can enhance the performance in the downstream task. So this paper is called GFM-RAG, Graph Foundation Model for Retrieval Augmented Generation. So the code can be accessed from this kind of QR code. So yeah, let's start with some background, like why we need this kind of like enhance the LM with the power of the graph and also the power of graph foundation model. So the large language model, even though they have been pre-trained with lots of corpus, they have been criticized for lack of up-to-date and domain-specific knowledge. For example, if we ask like what product did Apple release this year, the LM might say, okay, I do not have the knowledge, so I cannot answer your questions. And also this kind of situation can also happen when we apply the LM to some domain-specific tasks. For example, some medical question answering or some legal question answering, the large language model might not have the specific knowledge in that domain to correctly answer your question. So in order to solve this kind of limitations, the existing work try to there's a lot of practice we can use, and the most like commonly used method is called retrieval augmented generation. So basically, for the retrieval augmented generation, we try to retrieve. So given a user a question or query, we try to retrieve some knowledge from some kind of like documents or database. So this kind of knowledge will be injected into the context of the LM. So that, for example, given a query, we can retrieve some relevant document, and we provide the LM with such a knowledge and ask LM to, based on this kind of knowledge, to answer the question. So this kind of RAG pipeline has proven effective in integrating the new knowledge into the LM without the heavily retraining of the model parameters. So the key point of the RAG is there are two key components in the RAG system. So one is called indexing and one is called retrieval. So for the indexing, basically we utilize some kind of like embedding model to generate some representation for each document. Then in the retrieval part, we will utilize the same embedding model to generate the representation of the query. Then we can calculate the cosine similarity with the index we build. So most of the existing RAG system adopt this kind of like dense embedding based index. And then we can retrieve the documents by calculating the embedding similarities. So here is an example for documents. We use embedding model to generate the embedding and we store in a vector database. Then for a user's query, we calculate the similarity and retrieve the relevant documents and give the LM such a documents to do the generation. So one limitation of such a pipeline is like it usually ignore the relationship between the knowledge or between the documents. So this limits their performance in some intricate reasoning that requires integrating knowledge from multiple sources. For example, if you are a lawyer, when you deal with some kind of legal cases or legal questions, you usually require to refer like like the cases from knowledge from multiple legal cases to better like answer some kind of legal questions. So the relationship between the knowledge can be very important for this kind of like complex reasoning task. So existing methods fail to capture the relationship between the documents and cannot understand like why they are related because they're purely based on the embedding similarity. So this makes like this kind of dense embedding based RAG cannot like achieve like suboptimal performance in some domain specific tasks, for example, legal, finance, or medicals. So and also another thing is like most of the like for lots of like complex reasoning questions, they cannot purely based on like a single step RAG. They usually require like a maybe we need to like decompose a task into multiple steps, and we need to like answer this kind of question like step by step, which means that we need to like retrieve the relevant knowledge and in each step. So it will be like an iterative like multi-step reasoning. However, like even though there are some existing attempts to do this kind of like iterative RAG, but this kind of iterative RAG suffers from the high computation and the latency. Because in each step, we require the LM to do the generation and to generate a subquery. Then we utilize the RAG system to retrieve like intermediate answer. Then based on the intermediate answer, the LM will do the generation again and generate a next step query and do the retrieval and the generation. So this kind of like iterative process require lots of like computational cost and multiple like API inference. So they cannot be very efficient for solving this kind of complex reasoning question. Yeah, so recently there is a popular new paradigm called graph enhanced RAG, in short of like graph RAGs. So instead of only utilize the embedding model to construct the index of the documents, the graph RAG focusing on construct a graph structure to explicitly model the relationship between the documents. So this allows us for more effective and efficient retrieval. So there are lots of ways to build a graph structure that models the relationship between the documents. For example, if we have like a Wikipedia pages, we can utilize a hyperlink between the pages to build the graphs. Or if we have like an academia graph, then we can utilize the reference relationship between the papers to build the graphs. Then based on this kind of graph, we can design some kind of like retrieval system that better utilize the relationship between the documents to find the relevant information or knowledge and utilize and provide the LM with such a knowledge to conduct the reasoning and the generation. However, one limitation of such a graph is like this kind of graph only provide a very cross relationship because they are focusing on like the document level information. But for documents, it contains like it can involve multiple different knowledge. For example, for Wikipedia pages, like in different section, you can describe like different things. So this kind of a cross relationship might not well represent or capture the relationship between the knowledge. It only focusing on some kind of like document level relationships. So recently, instead of utilize the document level like graph structure, we utilize for now. There are lots of researchers focusing on utilizing the graph, a knowledge graph as the index. So the knowledge graph actually can provide a structured index of knowledge across multiple documents. It can provide a more fine-grained relationship between the knowledge. So consider we have like, for example, we have 4 different documents. They all describe something about like Barack Obama and the United States. Then for each document, we can extract the triples, like basically the facts mentioned in each document. Then based on these facts, we can construct a knowledge graph. So we can utilize some open information extraction tools to extract a knowledge graph. Then we can see that even though this kind of facts are separately stored in different documents, in the knowledge graph space, they are densely connected, which helps us to better capture the relationship between the documents. For example, for the United States, even though they have been mentioned in different documents separately, but in the knowledge graph, they can be mapped into the same entities. And also, there are also lots of relevant facts related to the United States can be closely identified from the knowledge graphs. So right now, the knowledge graph, because it can provide this kind of like fine-grained index of knowledge, they have been widely used in the graph rack to help us better capture the relationship between the knowledge and utilize it for the retrieval augmented generation. So like there are some existing study focusing on utilize the same pipeline because, for example, the graph rack presented by the Microsoft, and they focusing on the kind of like a summarization task. So based on given like a set of original document, they first built a knowledge graph from this kind of like original documents. Then based on the graph structure, they will utilize some community detection mechanisms to cluster the documents into several communities. So based on each community, because this kind of knowledge are densely connected in the graph structure, so they basically describe the same things. So they will generate some community level summarization. Then you can, during the generation step, we can retrieve both the community level summarization and also the original documents. And you provide such information for the summarization. Because like we already generated this kind of community level summarization, you can better like simultaneously consider like multiple document information and enable a better summarization performance. So this shows the power of the graph structure in the RAG systems. And another paper called HyperRAG is focusing on the multi-hop question and answer task. So like the example we have discussed before, like there are lots of like real world questions require like multi-step reasonings. So instead of like ask LLM to decompose the questions and do this kind of retrieval step by step, the HyperRAG actually try to utilize the graph structure. Then it will utilize the graph structure to capture the relationship between the documents. So you can easily retrieve like multi-hop retrieve the documents like maybe like multi-hop of like that in a multi-hop distance from the questions that can directly answer the user's problems. So what they did is actually you will utilize a method called personalized page ranks. So it will identify some signals based on the user's questions, and then it will utilize a personalized page rank to consider the importance of other documents with respect to this kind of given question entities. So basically, it will utilize the graph structure to identify the most similar documents from the graph structures, so that we can retrieve this kind of documents and and return it back as the relevant knowledge to help the LLM to answer the question. So basically, instead of using the LLM to do this kind of sub-query generation, you will utilize the graph structure to directly retrieve like the multi-hop documents. So it can be helpful for this kind of like multi-hop question answering task. So these two examples shows the power of the graph structure in the RAG system. So how we can utilize graph structure for this kind of like a global level summarization or multi-hop question answering. However, even though the graph structure are very helpful for this kind of RAG system, there are still some limitations about the knowledge graphs. So the first is like construct a knowledge graph can be very challenging because the knowledge graph can be noisy and incomplete. So this kind of like if the graph structure are not that good, then they might not well represent the relationship between the knowledge and leads to a suboptimal performance. And the second is during the retrieval stage, how we can do this kind of retrieval how we can design like a retrieval mechanism that can better capture the graph structures and retrieve the relevant documents. For example, the conventional embedding similarity might not works well to consider the graph structure information. So that brings to the problem is like how we can effectively utilize the graph structure during the retrieval. and how can we handle this kind of noisy graphs to effectively find the relevant information. So in order to consider of this kind of graph structure, we require to do some reasoning on the graphs. So the graph neural network have demonstrated like impressive performance in the graph due to its powerful graph reasoning abilities. So here is a paper called GNREG. It actually is the first paper that combines the power of graph neural network and graph reasoning abilities with the LLM. So given a user's question, it will use the graph neural network as a reasoner to consider the graph structure to to predict some candidate answers. Then this kind of answer together with some shortest paths from the knowledge graph will be returned to the LLM to help LLM to generate the final answer. So because like graph neural network has shown very powerful graph reasoning ability, it can already generate some very high quality answer that can be helpful for the final answer generation. However, despite this kind of powerful method, the power of the graph neural network, the existing works fail to design like a general graph neural network or foundation graph neural network that can be directly applied to a new data set or new knowledge graph without further training. They usually require like to retrain the model from the scratch on a new document, on a new knowledge graph, on a new data set, which is not like a design properties, because we usually we want to have like a more general retrieval model that given a new set of documents and a new knowledge graph that we can directly apply our model to retrieve some knowledge without like retraining from the scratch. So to achieve such a goal, we need to design a graph foundation model from the large scale training that can be generalized to like different graph and different documents. So there are existing attempts try to design such a graph foundation models. So what they did, actually, they usually try to find some transferable graph tokens that can be directly generalized across different graphs. For example, they can be some kind of like a relation graph in the knowledge graph, or some kind of like base graph structure like motif or like triangle, this kind of information. However, this kind of existing attempts of developing a graph foundation model only focusing on tasks related to the graph learning, such as node classification or link predictions. So the approach of integrating the graph foundation model with large language model to enhance its reasoning or to utilize it for the graph RAG, driven by both of these models haven't been explored by existing studies. So that is reason why we need to design a graph foundation model that can help the LLM and also help the performance under the retrieval augmented generation. So to address this kind of like research gaps, we propose a novel graph foundation model, which is powered by a graph neural network for retrieval augmented generation. So given us like here is like a very easy framework of our overall framework of our method. So given a document, given a set of documents, we can construct a knowledge graph as an index with some open information extraction tools. And then given the user's query as input, we can feed it together with the knowledge graph into our graph foundation model retriever, and it will conduct the reasoning on the graph structure to retrieve some relevant documents from the original document sets. So this kind of relevant documents will be together fed with the question into the LM to generate the final answers. So our graph foundation model actually is trained with large scale pre-training around like 60 knowledge graph with over 40 million triples. So after this kind of large scale pre-training, it not only shows the great performance, but also shows a great generabilities. So it can be directly applied to an unseen knowledge graph without any training, and it has shown a very good performance to retrieve the relevant knowledge. And what's more, because we claim it as a foundation model, it has shown this kind of like follows the narrow scaling law, which means its performance will increase with more training data and even larger like parameter size. So let's go to more details about our method. So for the knowledge graph construction or knowledge graph index construction, we just utilize a large language model to do this kind of works. So given like a document, we just provide a short instruction. So to ask the LM to extract the triples mentioned in the documents. And also for some like entities, because like the same entity can be described in different ways in different documents. For example, it can be like United States, US, or USA. So we use to address this kind of like a different representation of the entity. We also utilize some kind of entity resolution tools to calculate the embedding similarity and link this kind of entity with similar semantics. Yes. So definitely, our method here just present a very naive way to construct a knowledge graph from the raw documents. There are also any other like more advanced knowledge graph construction method or tools we can use, but we just leave it for the future like research because our methods is majorly focusing on the graph foundation model. So ideally, you should be able to handle with different knowledge graphs, even though sometimes the quality of the knowledge graph might not be great. Yeah. So here is the detailed framework of our method. So in the first step, given a set of documents, we already extract the triples mentioned in each document to construct our knowledge graphs. So here we have is like mentioned entities in each documents, in each documents. So based on this kind of like entity mentioned relationship, we can construct this kind of like an inverted index. Basically, it shows like how entities is mentioned in each document. So in the end, because we want to go back to the original documents, so we need to utilize this kind of like inverted index. Then for the graph foundation model, given a user's query, we first like extract the mentioned question entity from the user queries. So for example, Barack Obama is a politician of which country? Then we can extract a question entity is Barack Obama. Then in the graph neural network, basically we try to conduct some graph reasoning. We want to identify, the basic goal is like we try to identify some knowledge that's relevant to this query. For example, maybe the answer is like is USA. Then we try to capture this kind of relationship between the user's query and also the knowledge basically is entity in the graphs. So in order to capture this kind of relationship, we utilize a graph neural network and powered by like multi-layer of message passing. So here for the question entity, for the entity like mentioned in the question, we initialize its embedding with this kind of with some kind of sentence embedding model. Basically, we initialize the question with the sentence, we feed the question into the sentence embedding model and get a question representation. Then we initialize the question entity with the question embedding, and all the other entities are initialized with all 0. Then we can conduct like a multi-layer of message passing powered by the graph neural networks. So basically, it can be the basic goal is like we try to propagate the information, the question information from the query entity to all the other entity in the graphs. Then we try to capture their relationship with the query by considering the structural information in the graphs. So basically, after multi-layers of the message passing, we can conduct this kind of like multi-hop reasoning on the graphs, then better estimate its relevance to the query. So in the end, for each entity in the graph, we can calculate entity relevance scores. So this estimate how relevant the entity is to the query. So here we can see that the most possible answer is USA, so it gets the highest relevance scores. Then this kind of entity relevance scores will be fitted together with the inverted index. Basically, if for each document, you can have like multiple involved entities. So if documents contains lots of entities with high relevance scores, that means that okay, this document definitely is highly relevant to the user's query. So basically, we will utilize this information in our document ranker here. Then we will retrieve the relevant documents and feed it together with the final question into the LLM to generate the final answer. So here we can see that we combine the power of graph neural network to conduct the graph reasoning and also retrieve the relevant document and utilize the LLM to reason the final answer. And basically, the model, because we conduct like large-scale training of our foundation model, and the training object of our GFM actually is to predict the target entity given the query. So the model can be optimized by this kind of two training losses. The first one is like given the query, we want to maximize the probability of the target entities. And the second one is like to avoid the like gradient, because we only have very few entities in the knowledge graph that have been considered as a target. So to avoid the like gradient vanish problem, we're also utilizing some kind of ranking loss to improve the performance of predicting the target entities. And we conduct the training we conduct a two-stage training. So for the first stage, basically we utilize some kind of self-supervised KG completion pre-training. So we sampled lots of triples from the knowledge graph as the syntactic query. And for example, Barack Obama was born in Honolulu. So we sample the triples and we can mask out the tail entities and only utilize the head entity and the relation and query as input. And we try to predict the tail entity as the target one, so that we can automatically sample lots of queries from the knowledge graphs. And in the second stage, basically, we utilize some like labeled question and target pairs. So we can have some questions, and also we feed this kind of natural language as input into the graph neural network. And in the output stage, basically, we extract the mentioned entities in each document, and we are trying to maximize the probability of predict this kind of target entities in the supporting documents. So undergoes this kind of two-stage training. We pre-train our method on very large-scale data set with over like 60 different knowledge graph and 40 millions of triples. So undergo this kind of large-scale training, our method exhibits a strong generalizability, which means that it can be directly applied to a new knowledge graph without any training, and it can directly, given a query, you can directly retrieve the relevant documents and utilize it for the LLM reasoning. Yeah. So here is some experiment result we have conducted. So first, like we compare the retrieval performance of our method and also some existing retrieval mechanisms. For example, we have compared with some single-step embedding-based method. Basically, it will directly calculate the query similarity, the similarity between the query and the documents, and retrieve the relevant documents for the question answer. And because this kind of like three data set we evaluate is like a multi-hop question answering data set. So this kind of naive single-step retrieval can lead to a very poor performance under these three benchmark data sets. And also there are some existing graph-based mechanisms, because we can see, for example, the HippoReg, because you consider of the graph structure information, so it can directly retrieve like more relevant information, even though they are not directly even though they are not like semantic similar to the user query, because they are structure connected. So we can retrieve this kind of relevant document and improve this kind of multi-hop question answering performance. And also we have some kind of like a multi-step mechanism. Basically, we can combine the power of our retrieval mechanism with the large language model. So the LLM can break down the complex question into multiple like simple question. Then we can retrieve like the relevant knowledge for each subquery. So we can see that even though this kind of multi-step framework can improve the performance of the existing method, but it still cannot achieve against our baseline method, even though we only conduct this kind of like single step retrieval. So we attribute this kind of performance to the power of graph neural networks. Because with this kind of multi layers of message passing, we can effectively conduct this kind of multi-hop reasoning, even though within like a single step reasoning. So we also try to compare the question answering performance. Basically, our method, even though with the power of graph neural network, we can conduct this kind of multi-hop reasoning within like a single step reason within a single step retriever. We can still combine our method with the large language model to harness the ability of both the graph reasoning and also the LLM reasoning. So here we can see that we can also conduct this kind of multi-step retrieval and question answering. So we can ask LLM to decide whether there are enough information for us to answer the questions. So if there is not, then we can try to like retrieve more information. So we can see here, by combining with this kind of multi-step framework, we can further improve the the question answering performance. So this shows like the compatibility of our method with this kind of existing multi-step frameworks. So we can harness the ability, the reasoning performance of both the graph reasoner and also the language reasoner. And here we show the efficiencies of method. So like we have talking about like the existing multi-step framework, because they require the LLM to do this kind of multi-stage retrieval and decision making. So it have lead to a very high like retrieval times. And also our method, because it purely based on utilize the graph neural network to conduct the multi-hop reasoning on the graph structure. So it will be more efficient than existing like LLM-based multi-step methods. So you can achieve like great efficiency in performing like multi-step reasoning in a single steps. So here we also initialize like whether the graph neural network can actually successfully conduct the multi-hop reasoning by capture the important reasoning paths lead to the answers. So actually we can visualize the capture path importance to the final predictions by quantify the partial derivative of the prediction scores with respect to the triples at each layer. Basically, for the multi-layer message passing, we can like visualize which triples is focused by the graph neural network in each steps, so that in the end we can formulate a full path, like starting from the question and end as answer. And we can see here, we can find the graph neural networks can actually identify some meaningful paths that can be helpful for answer the questions. For example, what football club was owned by the singer of these songs? Then for the path we capture, we can find it. We can first find this, like this song is a song by the singer, and this singer has a football club named after it. So that is the football clubs for the answers. So basically, our graph neural network can successfully conduct this kind of multi-hop reasoning with its like multi-layer of message passing. And also, because we claim our method as a foundation model, so we definitely need to test its zero-shot generalizability to unseen datasets. So we further conduct experiments on 7 domain-specific like question answering datasets. So there are some kind of biomedical knowledge graph question answering biomedical domain, and also customer support, and also some general knowledge datasets. So we evaluate our method on this kind of 7 domain-specific dataset, and we can see that our method like significantly outperforms the existing graph-based method, like for example the HippoReg and also the LetReg. So that shows the generalizability of method across different domains and generalize to new datasets. And the last is like, because we want to test as the foundation model, can our performance increase or scale with the data and the parameters? So here, as shown in this figure, we test, we can see the performance of method can scale well with the parameter size increasing and also the training data size increasing, and it can be well fitted under the like a scaling laws patterns. So this shows that if in the future, if we provide more training data and utilize even larger parameter size, maybe we can have like a more powerful graph foundation model that can show better performance in the graph reasonings, and it will lead to a better performance in the downstream task. Yeah, so that's all for today's presentation, and thank you everyone for the listening. And so if you have any questions, please ask, and we can have some kind of discussions.
Thank you very much, Linhao, for this talk. I'm sure we're going to have questions in the rooms or in the room or online. Who want to start? Okay, so vas-y Tanguy.
Okay, thank you first. A few slides back, when you were talking about training the GNN for your specific index, do you retrain it for every new relation or new entity you add to your graph, or is it like, does it have some kind of flexibility, or do you really need to retrain each step? And at the same time, if you have contradictory information, for example, entities, it's also linked to some kind of space or temporal relationship, is it good enough, or does it fail to choose the most relevant ones according to the question, or is it just focused on the relevance at one point in time?
I think yeah, thanks for the question. So I think the first one is like, given a new knowledge graph with new entity and relation, do we need to retrain our model for it? Is that correct?
Okay.
Sorry, if I understand the question correctly.
Yes, the first question was okay. Yeah.
Yep. So in this case, so definitely the first answer is that we do not need to retrain our model, and the reason is like we handle this kind of unseen relationship by utilizing this kind of like sentence embedding model. So basically, given a new relationship, we can utilize the sentence embedding model to capture its semantic information and then represent it as the same dimension here, so that our LM can map it, like we can map this kind of unseen relationship into the same dimension space. So we can directly apply our graph neural network to consider this kind of a new semantic information and also the structure information to conduct the reasoning. And we will do the same thing for the questions so that they are in the same semantic space. So we do not need to retrain our model again for the unseen entity and also unseen relationships.
Okay, and if you have contradictory information in your graph, for example, temporal relationship, someone was governor at some time, then it's another person.
Sorry, I might not understand question. So is your question like, do we consider some kind of like temporal informations in the knowledge graph?
Yes, and if they revert or evolve according to time. For example, you have one document from 2015, one from 2021, and you have different people having the same function. Is it okay to put contradictory information there?
Yeah. I think that is a good question. I think for now, we do not consider this kind of like temporal information in the graph. We only assume this is like a static knowledge graph. So we do not consider like the temporal information or timestamp. But I think this information definitely are very important, and maybe they require some modifications to the graph neural network structure to better capture this kind of temporal information. Yeah, but thanks for the suggestion. I think that's definitely a very good things to study in the future.
Thank you.
Yeah, thanks for the question.
So kind of a follow-up question to this one. So about temporal information, I think it's pretty standard to not consider it in a knowledge graph. But here, since it's a knowledge graph built on the documents, you might still have information that is contradictory or even false. Do you think that in that case, your method makes something that's as good as the data set and you just fall into the same mistakes? Or do you think that there's something in the LLM or in the method that might compensate for that?
Yeah, that's a good question. I think the short answer is that yes, we believe our method have shown this kind of ability to compensate to the noise in the data, because that is one of the major motivation why we need to utilize some deep learning model to conduct the reasoning on the graph structures. Because like you mentioned, the graph we constructed can contain some noise information or contradict or incorrect facts information. So if we purely rely on the structure or the knowledge in the existing graphs, it can lead to this kind of errors and can lead to some incorrect answer. So by incorporating the graph neural network, we believe our method shows the ability to conduct the reasoning and identify the meaningful information not purely based on the structure, but also consider the semantic information in the graph and also estimate its relevance to the questions to generate the final answer. So we believe the neural network have such abilities to handle this kind of noise in the original data. And also we can combine this kind of abilities with the large language model. So if the LM can design, okay, if the retrieved knowledge is contradict to its internal knowledge, maybe we need to reject this kind of retrieved result. We need to do the retrieval again, and then we can have a better performance and solve this kind of noise information in the original data. Yeah, I think that's it.
Hi, thank you for your talk. I was wondering, are there any cases where no document is considered relevant enough to be ranked, or do you always have a ranking of some of the most useful documents, and the LLM later has to do the job of rejecting or saying no document is useful? Like, where does the rejection happen?
Yeah, I think that's a good question, but I think unfortunately we haven't studied these problems in our works. But I think yeah, in some kind of existing some existing works try to combine the reasoning of the RAG. For example, there's a work called search R1 or research RE search. So this kind of mechanism try to combine in their work. They try to combine the reasoning of LM with the retrieval with some kind of retrieval to retrieve the document. So in their study, they have shown that when the retrieved document is incorrect or irrelevant, the LM will automatically reject this kind of retrieved documents in the reasoning process and do the retrieval again. So I think this their experiment shows that LM has this kind of certain abilities to maybe dynamically adjust the retrieved documents and to enable a better performance. So our method basically here have shown a very toy example to see how can we combine our method with the LM. So if the LM can find, okay, this kind of retrieved document are not relevant, then maybe we need to maybe some kind of revise the questions and retrieve some new information for the question for the final answer generation.
Okay, thank you.
Yeah. Thanks for the question.
Any question online? Okay, you have questions? Not you. Okay. So if we get if we go to your QR code and we get the model, so what do we get? If I want to have some fun and try to apply that contribution to some knowledge graph we have and play, what do I get? I get the full model with all the parameters. What do I get there?
So basically, we already released the pre-trained model and also the training framework in the GitHub. So if you go to our paper, you can access the GitHub of our method. We already released this kind of pre-trained model. So basically, means that you can already directly like download it and apply it to your like your own knowledge graph to try to do do some like question answering. So you can feed your question into our model with your knowledge graph, and our our GFM model will predict maybe the relevant entities or relevant documents based on whatever you need. Then you can utilize this to design retrieval systems to help to answer the user's questions. You do not need to conduct any training, but you can further improve the performance if you can further fine-tuning the models on your own data set. So if, for example, if you have some question and answer pair or question and a supporting document pair, you can definitely keep fine-tuning our model and get a better performance on your own data sets. So we have released the full training pipeline, so you can already utilize for fine-tuning.
Okay. And I guess you are building the knowledge graph from the documents you analyze, but sometimes an external knowledge graph like an ontology can come also in addition to those documents. Is it possible to feed this external knowledge source into the system?
Yes, definitely. So I think you can definitely utilize your own knowledge graph to conduct the reasoning. And also, if you do not, so if you check to the framework, you can see here. Basically, the knowledge graph and the document are separately used in our frameworks. So if you're only focusing on some kind of like knowledge graph question answering, so you can definitely just use the knowledge graph you have. And given the question, you can predict the tail entity as the answer. And also you can build like the connection between your knowledge graph and the documents with this kind of like inverted index. So you can find your own way to map the relevant entities to the documents, and also to or maybe to other like knowledge source you have to find the more useful information. So you definitely you can combine the power of our methods with any knowledge graph or documents or knowledge you have.
Okay. This is neat. Okay. Any other question around? No? In this case, we want to thank you again, Linhao, for this brilliant discussion this morning. And I'm sure we are going to jump into your code just to make an idea and play a bit with that. And I'm going to contact you later on to carry on with the discussion.
Yeah, sure. Yeah, thanks for the invitation.
Thank you.
Bye-bye. Bye.